Hello and welcome to our second lecture in the series on random variables and probability distributions for our course Introduction to Data Analytics. In the previous lecture, we saw we made a more broad introduction to the concept of random variables and distributions. We spoke about the concept of having continuous distributions and discrete distributions. We presented some examples, and we also spoke about the idea of a probability density function versus a cumulative density function. In today's lecture, we are going to pick 5 or 6 very common distributions and discuss them one at a time. And the first one and these distributions are going to be both. Some of them are going to be discrete, some of them are going to be continuous, and some of them could be both. So we start with the most common distribution, which is the uniform distribution. The uniform distribution has a discrete version and a continuous version. Now we'll start with the most simple one, which is the discrete version. You've already seen examples of this. So for instance, the example that we saw in the last class of a 6-sided dice, where we were quantifying the probability of getting any particular face value. So the face value of the dice is essentially you throw the dice, you get something on top, right? So it's either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So the probabilities associated with these 6 possible outcomes, assuming a fair dice, is 1/6 for each. And so that's an example of discrete uniform distribution. We also saw the case of the coin toss, where here you have only 2 possible outcomes, and as long as they're both equal, it's still uniform. So the formula in terms of the PDF, the probability density function, which we discussed in the last class, is fairly straightforward. It's just 1 by k when there are k outcomes. So if there's a 6-sided dice, it's 1 by 6 for each of those 6 possible outcomes. If it's a coin toss with just 2 possible outcomes, it's going to be 1 by 2. And the idea is that for each of those k possibilities, it's 1 by k, and for the rest of the universe, it's 0. So the probability of getting a 7 when you roll a single 6-sided dice is 0. So you cannot get 7, and you cannot get minus 45 either. So that's what this formula says. With the continuous version, you're looking at a uniform distribution. So the probabilities are uniform, but like we discussed, the variable that we're quantifying, right, is continuous. So the variable in the 6-sided dice was what is the number that shows up, and that number is either 1, 2, 3, 4, 5 or 6, and that's 6 discrete possibilities. But you might have many things that are not discrete, and this goes back all the way to our discussions on quantitative variables, which can be continuous or discrete. So examples of this, and the truth is, the uniform distribution, while it's theoretically very intuitive, could be quite convenient in some cases, there aren't a lot of examples, real world things that tend to be uniform. Some of them are something like the number of seconds past the minute. So if you were to randomly if you were to have some random process which just looked at the clock over the course of the day during some random intervals, the number of seconds past the last minute could be uniform, and that's essentially a space where you could have 0 seconds past the minute all the way to 60 seconds past the minute. So your interval is from 0 to 60, and where you find yourself in that interval is described potentially by uniform distribution. And again, the idea that it's continuous just means that you've not discretized the seconds as 1 or 2 or 3 all the way to 60. You could be in 4.5432 seconds past the minute. So it's a continuous. The variable time is being monitored continuous as a continuous variable. Another example, it could be the exact age of a randomly selected person between the ages of 50 and 60, perhaps in a certain country. Now, again, you have to come up with fairly specific examples, because something simple like the age of a randomly selected person is not likely to be uniform. You're not likely to find as many people between 80 and 90 as you are between 70 and 80. And even if you stop the clock at a certain point, typically with things like age, you see that the number of people, or the probability of a person in that window, decreasing as sometimes age increases. And it depends on your state space, it depends on your country, is the population increasing, decreasing, so on and so forth. But sometimes over a short enough interval, even if the overall distribution is not uniform, you can create an interval and say that's my universe. So my universe is people between the age 30 to 40. Within that interval, perhaps the distribution of the exact age of people. So imagine I take the universe of all people between the ages of 30 to 40 in India, and then I try to create a distribution of the exact age of a randomly selected person from this bucket, and that could potentially be uniform. The uniform is also a great distribution to think of when you want to make absolutely no assumptions, right? So if I were to make the assumption that the country's population is and some of these need not even be assumptions, they could be facts, but something simple like the country's population is increasing, and so on, then I would be hard pressed to come up with a uniform distribution. I might find a richer distribution to represent my data, but this uniform distribution can be thought of as like this ground zero. I don't make any assumptions. The probability of everything occurring within a certain interval is equal, and so I could potentially use it. I've also come across the usage of this a little bit in different aspects of like physics and chemistry and so on. For instance, the probability of certain types of molecules being in certain locations over a certain space could be uniformly distributed and so on. Okay, so we've spoken about so the formula for the uniform distribution. We spoke about the discrete uniform PDF, and we said the PDF is essentially 1 by k, right? So with the continuous, the PDF is essentially 1 by b minus a. So the idea here is that this is essentially a, and this is essentially b, and as you can see in the graph, the probability between a and b is uniform. And just like in the discrete case, if this distance is b minus a, then the probability is 1 by b minus a, right? And another quite simple way of thinking about it is between this interval, right, over this entire interval from the lower limit to the upper limit, the area under this curve should be equal to 1. And if you look at the simple math of it, 1 by b minus a times b minus a, which would be, so the height is 1 by b minus a, the length of this rectangle is b minus a. So 1 by b minus a times b minus a would give you 1, and so you can essentially think of it that way as well. And obviously, like we discussed, it has to be 0 for if you're less than a or if you're greater than b. Okay. So what is this CDF of this distribution? Again, it's x minus a by b minus a. We won't be exactly deriving it. We will give you formulas at the end of this lecture to give you an idea of how to get to the CDF, how to get to the mean, how to get to the variance. But the core idea here is that essentially you take some point, and let's call this point x. Okay, so this is x. There, better x. And the whole idea is that we know the CDF is essentially the area under the curve to the left of x. So the question could be, if you knew that this height is 1 by b minus a, how do you go about writing out this area? How do you calculate this area? And it can be a function of x, and so that general formula would be the CDF. And the idea is fairly simple. If this is x, and you're looking at the CDF is a ratio. It's essentially the area. We know that the total area is 1, right? So this total area of the blue rectangle is 1 that we've discussed. So what percentage of that rectangle have you essentially covered? And the idea is, because it's uniform, because this height is constant, if this is x and this is a and this is b, then of the 1 you've covered, x minus a is this area that you've covered, and b minus a would be the full area that you could possibly cover. So if you think of it as a ratio of how much I've covered to how much I can potentially cover, where this b minus a kind of represents the 1 in some sense of the full area, then I've covered x minus a of the b minus a that I could cover, and therefore I've covered that percentage in some sense, where obviously if x was equal to b, if this was equal to b, if x was equal to b, then I would have covered the 100%, and that would be equal to 1, right? So that's the overall idea behind getting this formula. Again, the formula for the mean should be fairly intuitive. If this is a and you have this as b, the central point in some sense is b by half of between b and a, essentially. And again, with variance we won't derive it, except to tell you that the core concept is to say how much do we deviate on average from the mean. So we'll talk through some of these formulas. Some of it is to give you an intuition, some of it is to actually give you these problems in the assignment, so you get a feel for actually figuring out what the mean or variance exactly is. Okay, so let's move on to the next distribution. The next distribution we're going to talk about is the binomial distribution. So the binomial distribution is also another distribution where you have a lot of toy problems associated with it, but by nature of it, in the real world sometimes it's more useful to approximate it with another distribution and use it. But what exactly is the binomial distribution? Let's start there. So we spoke about this class of distributions, and if we didn't, let's do that right now. So there are these class of distributions where called the Bernoulli distributions, and the idea behind that distribution is that it's very similar to the first example we saw in the previous lecture, where you have an event and it has some probability. So there's a 30% chance it's going to rain. That was the exact example we used. And so therefore the probability that it's not going to rain is 70%. What's key about it is that there are only two possible outcomes, and these two possible outcomes, discrete outcomes, sum to 100%. And that class of distributions is called Bernoulli distributions. So a standard example of tossing a coin and saying what is the probability of heads and what is the probability of tails would be an example of a Bernoulli distribution. Now, if, just so that there's no confusion, if it happened that the probability of heads and tails are both equal, you can also think of it as a discrete uniform distribution. But out here we're saying something different. We're saying that Bernoulli distributions are distributions where there are only two possible outcomes. The probability of the two outcomes need not be the same as required by the uniform, but the key out here is that there are only two possible outcomes, two possible discrete outcomes that sum to 100%. Okay, so great. So we've spoken about the Bernoulli distribution. What does it have to do with the binomial distribution? Isn't that what this slide is about? Well, if you take the problem and you quantify the probability of heads and tails, then you're talking Bernoulli. But instead, if I rephrase that problem and said, what is the probability of getting 5 heads out of 10 tosses, then I'm describing the problem associated with a binomial distribution. So an example of a binomial distribution would be if I said I'm going to toss the coin 10 times. I'm going to take part in a Bernoulli process, okay, n number of times, and I ask myself the question, what is the probability of getting k successes? And success could be defined as getting a heads or it raining, or whatever it is. It's one of those two outcomes. Essentially, you call one of those two possible outcomes of a Bernoulli process as a success, and then you say, what is the probability of getting k successes out of n possible trials? So if I say I'm going to toss the coin 10 times, can you tell me the probability associated with 0 heads, 1 head, 2 heads, 3 heads, 4 heads, all the way up to 10 possible heads? Now, note, if I toss the coin 10 times, I can either get 0 heads or any of those numbers in between till 10 heads. I can't get -1 heads, I cannot get 11 heads. So the probabilities associated, if I toss the coin 10 times, there's some probability that I'm going to get 0 heads. There's some probability that I'm going to get 5 heads. But each of these numbers, each of these probabilities when added together should again be equal to 100% or 1. So quantifying the probability of getting k successes out of n trials of a Bernoulli process is the binomial distribution. And you can think of various real-world examples. So, for instance, the probability of, let's say there are 10 mergers the companies considering. So, in mergers and acquisitions, since it's a small enough number, what is the probability of getting 3 out of 10 of them? Or you might say probability of having 5 defective products in a batch of 20 products. What's the probability of there being 3 defective products? Answering questions like that. And one just side note is, you might have noticed that I've taken examples with small enough numbers. So technically the binomial could be answering a question like, what is the probability that out of 1 million possible toys, let's say, that I distribute, I'm a toy maker and I send out 1 million, what is the probability that I get 5,000 toys as broken? And technically that would still be a binomial distribution, but what we will learn probably in the next class is why that the computation of that is a little messy. You get very large numbers, and you have some other distributions that can approximate something like this. To solve problems like that. But the core concept is this: you have a Bernoulli process where something is, you're looking at something that's binary, A or B, 1 or 0, and you turn around and you say, what is the probability of getting k successes out of n trials of this process? And so logically the formula, and note that I've used the word PMF out here. Okay, that's an important distinction that's worth mentioning. PMF is the same thing as PDF. PDF is probability density function. We spoke about that. We spoke about probability density functions and cumulative density functions. PMF is just the standard way of calling a PDF if you're dealing with a discrete distribution. And since this is a discrete distribution, right, because you cannot get, out of 10 tosses of a coin, you cannot get 3.5 heads. So that you can only get either 0 heads, 1 head, 2 head, or 3 head. And so since this is a discrete distribution, it's technically called a probability mass function, of PMF. So the PMF for this distribution should be fairly intuitive. It's nothing but n choose k. So this symbol out here just means, you might have seen it like this, right? So that's n choose k. And that has to do with a combination, something you might have studied in permutations and combinations. The idea is, how many ways are there of choosing n from k trials? So here I think the words n and k are swapped as opposed to what I was mentioning earlier. So here, for instance, if I was interested in finding out what is the probability of getting 5 heads, then it would really be 10 would be the n, c 5. So how many ways are there of getting 5, of choosing 5 out of 10? So I toss the coin 10 times. There are many ways in which I could get 5 heads out of 10 tosses. It's either that the first 5 could all be heads and the next 5 could all be tails, or you could have 1 head, 1 tail, 1 head, 1 tail. So the number of different ways in which I can get 5 heads out of 10 tosses is what is being quantified by this number, which relates to this part of the formula. Once I figure out the number of possible ways, this part, which is p power k, tells me what is the probability of getting the 5 heads in the first place. So it might be 0.5 power 5. If the probability of a heads was different from a tails, let's say we were dealing with a problem where 60% chance of heads falling because it's an uneven coin, then it would be 0.6 power 5, and this part, which is the remaining part, talks about the probability of getting the tails, the remaining 5 as tails. So essentially the 3 parts of this formula are the different ways of getting those heads, probability of getting so many of those heads, probability of getting the remaining number as tails. So that's essentially what the PDF captures. And the formula for the cumulative density function, again, it's the same logic that we were discussing with the uniform, which is that for a given k, which might mean, for let's say I'm interested in knowing what is the probability of 6 heads out of 10 tosses, you're essentially looking at nothing but everything to the left of the curve, and to the left of the curve here means what is the probability of getting 0 tails. So let's say what is the probability of getting 6 heads is the question out of 10 tosses, and that would be nothing but the PDF of getting 0 heads out of 10 tosses, 1 head out of 10 tosses, 2 heads out of 10 tosses, all the way up to 6 heads out of 10 tosses. That summation of those probabilities, because that's essentially what would be to the left of the curve. And here I'm doing nothing but thinking of a curve where 1 out of 10 tosses, we should start with 0 out of 10 tosses and going all the way to 2 dot 6, and then it'll go 7, and it'll go all the way till 10 out of 10 tosses. So this is if this was some kind of a PDF, I'm essentially looking for this area on the curve, and the top part of the line is not uniform. I'm just representing which side I'm interested in. That's all I'm doing there. And also it would be discrete, so you'll have discrete rectangles popping out of the 1, 2 and 3, and you're just summing them up. And the formula also with the summation does not really simplify too much, so you're dealing with the CDF as it is. As I mentioned, it is more useful for small values of n. When you get really large values of n, you look at other approximations. The mean is nothing but the number of times you're looking at times the probability. So if the probability of getting heads is 60%, right, and you were going to toss a coin 10 times, the average number of heads you're going to receive is nothing but 10 times 60%, which would be 6. So on average I should get 6 heads out of 10 tosses, because there's a 60% chance of getting a heads. And so the intuition of that should be fairly obvious. And again, with variance, the intuition itself might not be very obvious. It's really about looking at how much the deviation, how much of a deviation there is from the mean. So how much does 1 out of 10 deviate from the mean, and we'd look at the probability that you first of all see a 1 out of 10. And again, I think there the formulas for variance might probably help you get a better idea of it. Great. So let's move to our next distribution. This is also a discrete distribution, and this is very similar to the binomial in many ways. See, both of them are discrete, but essentially, while this is discrete, which also counts the number of possible occurrences, x. So it says this quantifies the probability of getting x occurrences. So the probability of getting 1 of those occurrences, 2 of those occurrences, but it is over a certain period of time or space. See, in the binomial we were saying what is the probability of 5 heads out of 10 tosses. So the 5 heads was discrete, but so was the 10 tosses. Here we're asking the question, what is the probability of x, where x is discrete, meaning, so what is the probability of there being 5 people? But instead we won't say out of 10 people, we will instead say what is the probability of there being 5 people coming to this bus stop over the next 5 minutes. The key difference is 5 minutes is continuous as opposed to 10 tosses, which is discrete. The ramifications of that is however low the probability is of people arriving in a given time, there is still technically a probability that you have a really large number of people, infinite number of people coming over the next 5 minutes. Whereas I can say with certainty in the case of the binomial that out of 10 tosses, I cannot get 11 heads. Right? And this has nothing to do with the probability of getting a heads in the first place. Even if I had a probability of 0.1 of getting a heads in a toss because it's such an unfair coin, I still know, or 0.9, whatever you want, whatever the probability is, I still know it's technically not possible to get 11 heads out of 10 tosses. Here you are looking at a discrete occurrence, such as probability that of n number of defaults in a given month, or number of people who are going to arrive at a bus stop in the next 5 minutes. The number of defaults, the number of people who arrive in the bus stop are discrete. You cannot have less than 0 people. I mean, in this particular case, you cannot have less than 0, and you cannot have 2.5 people who arrive at a bus stop. So it is a discrete distribution, but the distribution is defined over a time or a space which is continuous. So it's not how many heads can I get out of 10 tosses. It's more how many of a certain occurrence can happen over a certain period of time. And that's the core concept there. The PMF, again, note it's not the PDF because it's a discrete distribution, is characterized by lambda power k, and lambda here is a parameter. So it's essentially a number that you'll have, and it represents like the average rate. So if 3 people are arriving per minute, that would be more like a 3 out there. And k is the variable of interest, where you say k is equal to 1 and you get a probability. You say k is equal to 0, you get a probability. And technically this k can go all the way up to infinity, like I was discussing, right? And the sum of all those possibilities, discrete possibilities, is equal to 1, right? So if you wanted to know the probability that 3 people will arrive at the bus stand, all you'll do is you'll say, what is the average arrival rate? So maybe the average arrival rate, which is what is essentially represented by lambda. So the average arrival rate could be something like, well, 2 people arrive per minute. Okay, so that's 2. And I want to ask the question, what is the probability 0 people will arrive over the next minute? So I'd say on average 2 people arrive at the bus stop. K is that 0, right? So I'll just substitute k with 0, and this formula will spit out an answer which says the exact probability of 0 people. And you would replace k with 1, 2, 3, 4, and so on, all the way up to infinity, and the sum of all those probabilities is essentially what is essentially the distribution, is essentially what you quantify. Because of how it's defined, the mean is lambda, right? We define lambda as essentially that rate parameter, and it's an interesting property of the Poisson distribution that variance also is lambda, and lambda has to be greater than 0. But again, just to recap, the state space for a Poisson distribution, that is the possible values that k can take, are always greater than 0, 0 and greater, and less than, and goes all the way up to infinity. But it is a discrete distribution because you can never have 2.5 people arriving at a bus stop. Great. So the next distribution we're going to look at is the geometric distribution. The geometric distribution is also an discrete distribution, but it's a very interesting counterpart to the binomial distribution. So take the fact that we said there's a Bernoulli process, which means there's some probability of an event happening, some probability that the event will not happen, and they add up to 1. So probability of a heads, let us say, is 60%. Therefore, by definition, probability of a tails is 40%. Okay, that was Bernoulli, and then we said the binomial is nothing but the probability of getting k successes out of n trials. So what is the probability of getting 2 heads out of 10 tosses, 3 heads out of 10 tosses? That space is defined by the binomial. The geometric defines the probability of the number of times you need to toss the coin before getting your first heads. Or you can think of it as getting the next heads. So number of attempts before an event is what you're looking at, and therefore you can think of it as an inter-arrival counterpart to your binomial distribution. So if you take the coin toss case, right, essentially it's more like how many times do I need to toss the coin before I get my first heads, or the next heads. So you start at some point and then you say, okay, so obviously anything that I've tossed before does not influence my future tosses, because they're independent. And now I'm going to start tossing the coin, and tell me the probability that I will have to toss the coin 0 times before I get my first edge, or one. You can count. You can say what is the number of tails I'm going to see before I get my next head. So that could be 0, 1, 2, 3, and technically it can be infinity. Meaning there could be this really bizarre world where even though there's a finite non-zero probability of getting a heads, so whatever that number is, it could be 0.9 or it could be 0.1. It's technically possible that I wind up tossing the coin an infinite number of times. I keep getting tails, and so I'm still waiting for my heads. So this is again a distribution which starts with 0 and goes all the way to infinity, depending on how it's defined exactly. The geometric sometimes is defined as the number of tails you see before the next heads, and there the distribution starts at 0 because you can see 0 tails. Another version of this distribution could start with, instead, say how many tosses do you need to make to see the first heads. In that case, you need to at least toss the coin 1 time to see the heads, and so both these distributions you might find in textbooks. The PMF and CDF should be fairly intuitive. Out here, all we're doing with the probability mass function is saying what is the probability of getting k minus 1. Right, so here you might say k minus 1 is nothing but the number of tosses before the actual success that you keep getting the tail. So if p is the probability of getting the heads, you're saying what is the probability of getting k minus 1 tails, right? So if you, here we're defining the distribution as on the first toss I get the heads, then what's the probability that so let's say I want to know the probability of getting it taking 3 tosses before I get a heads. Then you're saying that means for the first 2 tosses, so 3 minus 1 is 2, for the first 2 tosses I should have gotten a tail. So what's the probability of getting a tail like that? And that's 1 minus p. So 1 minus p to the power of k minus 1 says before that success happens I need to see k minus 1 failures, and what's the probability of that, and then finally the probability of that one success, right? Again, essentially the CDF, you're doing a summation, but the summation kind of neatly simplifies to the formula that we've shown here, and the mean being 1 by p should be fairly intuitive, meaning if the probability of getting a heads is, let's say, 10%, right, it should be intuitive that it on average should take 10 tosses before I get my first heads. So 1 by 0.1 would be 10, and so on. And again, even if it's not entirely intuitive to you, you may be working through some problems and formulas where we will be discussing those can help. Finally, the variance is 1 minus p by p square, and even that's something that you might have to work through a couple of times. Okay, so we come to the last distribution that we're going to be discussing in this class, and that distribution is the exponential distribution. In many ways, the exponential distribution essentially, you know how the geometric was looking at the inter-arrival times of a binomial distribution? The same way the exponential looks at the inter-arrival times of the Poisson distribution. So what does that mean in terms of our examples? You know how we spoke about the Poisson distribution as being a discrete distribution, where you said what is the probability of 3 people arriving at the bus stop in the next 5 minutes, what's the probability of 2 people arriving at the bus stop in the next 5 minutes, so on. So you fix the time, 5 minutes or 10 minutes, whatever is of your interest, and you looked at the probabilities of various discrete possible occurrences, right? So you said what's the probability? 0 people arrive, 1 person arrives, 2 people arrive, 3 people arrive. Here with the exponential, you're describing the inter-arrival, that is, how long should I wait before the next person arrives. So it's the exact same thing. The exponential is the same thing to the Poisson, the way the geometric is to the binomial. The binomial is quantifying the number of the probabilities of getting 3 out of 10 out of 10 tosses, the probability of getting 3 heads, whereas the geometric is saying how long should I wait before the next heads arise. The Poisson is quantifying over some time scale or space scale. It's quantifying the probabilities of different occurrences, like what's the probability of 1 occurring, 2 occurring, 3 occurring. This says how long should I wait before the next thing occurs. So you can think of the exponential as moving in time and waiting for that next occurrence, and how long should I wait. Or you can think of it as space. I keep walking, and I encounter occurrences over some length scale. The Poisson gives me the probabilities of seeing n number of such occurrences. But if I start walking on that scale, how long should I walk before I get the next occurrence? And long can be in length or it can be in time. So think of it as time and space, but it's essentially the continuous version of the you can think of it as a continuous version of the geometric distribution. The more, again, the PDFs and the CDFs, it's there for your reference, but the important thing about this distribution is that people call it memoryless, meaning that the probability of something occurring over a time horizon, right, is the same if you condition that it's not happened yet. So think of it this way. I'm not saying, for instance, that so let's think exponential is often used to say to describe maybe the failures of a light bulb, okay, over time. So how long should I wait before this light bulb fails? Okay, whereas Poisson would describe saying out of 100 light bulbs over a 10-year horizon, how many would fail. But let's leave that. So out here in exponential, I'm dealing with one light bulb. I'm saying how long should I wait before it fails. So if this distribution were uniform, right, the probability that it would fail between year 1 and 2 would be the same as probability that it would fail between year 5 and 6. That would be uniform. What we mean by saying the exponential is memoryless is that the probability the bulb would fail between year 1 and 2 is the same as the probability the bulb would fail between year 5 and 6 if I tell you at the start of year 5 that the bulb has already not failed. So if you're standing at time 0, the probability the bulb will fail between year 1 and 2 is very different from the probability the bulb will fail between year 5 and 6. Okay? But the probability the bulb will fail between year 1 and 2 is the same as the probability the bulb will fail between year 5 and 6 if I go to year 5 and tell you that the bulb has not failed yet. Same way if I go to year 1 and tell you that the bulb has not failed yet. So conditioned on the bulb not failing, the probabilities over a future time horizon or length horizon would be the same. So great. And just for your convenience, I've kind of put together the 4 distributions that are partly related, and saying that these are discrete over the time arrivals versus how the distribution is counted. And I've used a color coding to describe which are continuous distributions and which are discrete. And you can see that clearly it's only the exponential that's continuous. The other 3 are discrete distributions. Great. Now before I sign off from this class, I just wanted to give you some formulas on how to calculate mean and standard deviation and so on. But before we do that, let's start with the more basic thing, which is, given a PDF, how are you going to get to the cumulative density function? And the idea here is, we've always said it's the area to the left side of the curve. So the left side of the curve is from minus infinity. So this is the PDF, right? And the left side extreme is referred to as minus infinity. Now if you know the distribution starts from another location, you just essentially want to get to the starting point. All this minus infinity means is the starting point of the distribution. If the distribution can technically go to minus infinity, it can. But like the uniform, for instance, it starts at A. So that would be A. You would replace that. And X is, you leave X as it is because your cumulative density function is a function of X. And this integral is what would solve it. Obviously, if you're dealing with a discrete distribution, you would instead have this summation, not integral. But everything else about this formula would stay the same. Okay. Same way, if you're going from CDF to PDF, you'll essentially differentiate the CDF, and there's not much more to that. Okay, so now coming to mean and variance. The idea here is that the mean x bar is the kind of mean that we've discussed so far. So you have some data points, you take them up, you average them, divide by. But if you want to start thinking of mean in terms of a distribution, so you're given instead the distribution, not actual data, or you use the data and created a distribution out of it, you created an f of x out of it, then how do you calculate the theoretical mean of the distribution? And that you do by essentially this formula for the continuous distribution and this formula for the discrete distribution. And these, you can call them expected values. These typically get called mu. It's that Greek alphabet mu. But the core idea here is that you take each possible outcome in the discrete case, multiplied by the probability that that outcome can take on, and we all know that these probabilities multiply all the way to the sum of these probabilities is going to be equal to 1, but you're multiplying pi and xi for each I, and that's the discrete case. The equivalent of that is nothing but f of x is the equivalent of pi and x is x in both cases. So this is the equivalent of the continuous version of the same problem. Okay, the standard deviation is the same. Here you had the n minus 1 because you were dealing with x bar, but if you have a theoretical mean that's given to you, you can use the n, and in the discrete case this formula, which is the same formula that you're used to with the exception of the 1 by n, takes place. Now this actually simplifies, and for your convenience on the continuous version I've given you the simplified version. This, to me, this version, which is used for the discrete, is more intuitive, but this formula simplifies to a formula which looks more like summation of x squared and so on. Separately, just like on the case of the mean, discrete uses a summation and the continuous uses an integration. We have the same distinction even here, but for your benefit, on this one I've shown you the simplified formula. So even here, originally you would have started off with integral minus infinity to infinity x minus mu the whole square dot f of x and so on, but that's not what we're doing here. And here actually this would not be dx, this would just be the probability, so it would be p of I out here, right? But out here it would be dx and it would be f of x because it represents that. So I hope these formulas give you some idea, and we will definitely be looking to see you apply some of these formulas on distributions to get answers. But that's it for this class. Next class we'll talk about the distribution that we have not talked about so far, which is the normal distribution. Thank you.